Hi there. This video is going to introduce our next system of interest, which is helium. Okay, so we just finished hydrogen, and we're going to move on to our next element on the periodic table, which is our friend helium. Okay, so helium has this beautiful Schrodinger equation that is shown right here. Okay, so this is the essentially the basic model of helium, right? We've got a proton and neutron in the nucleus, which gives us a charge of +2. Okay, and then we have two electrons, so electron 1, electron 2, which each contribute a negative charge. Okay, so we just translate that into a Schrodinger equation where we put together our kinetic energy terms. Okay, so these hopefully you recognize as our kinetic energy terms. Remember, the del squared operator is the shorthand notation for our kinetic energy. D squared dx, d squared dy, all of those terms, or in our spherical coordinates, okay, whichever coordinate system you're working with. Okay, so we've got one kinetic energy term that is associated with our nucleus. Okay, so that's our big M, right? And then we have one for our electron 1 and one for electron 2. Okay, so everything basically in our model gets a kinetic energy term. All right, and then we need our potential energy interactions that occur in our system. Okay, so we know that we have a few different types of interactions, potential interactions happening here. Okay, so we have our Coulombic interaction between our nucleus and electron 1, our nucleus and electron 2, and then also that interaction between our two electrons. Okay, so that is represented with our potential energy terms in our Schrodinger equation. Okay, so you can pull them out by their notation. So all the capitals, okay, whether it's a capital R or a capital M, okay, are referencing your nucleus. Okay, and then all the lowercase m's and r's are corresponding to your electrons. Okay, so this first term is going to represent the potential energy between your nucleus and electron 1. Okay, so from nucleus and electron 1, right? And then this second term is the potential energy or the Coulombic interaction, right, between your nucleus and electron 2. So that would be this Coulombic interaction. And then this third term is the Coulombic interaction between electron 1 and electron 2. So it's the electrostatic interaction between our two electrons. Okay, so let's just take a closer look at our signs here. So we have a negative sign corresponding to the first two terms, okay, which tells us that we should have an attractive force for those interactions. So we've got our positive and negative interactions between our nucleus and our two electrons. Okay, so those are going to both be negative interactions, so those lower our energy. Okay, and then hopefully you've all caught on to the typo that I have in here that I just saw. Okay, where we have an errant negative sign that probably carried over from a uncareful copy and paste. So we're just going to X that out there. Okay, so that third term is positive. Okay, so that tells us that we have a repulsive interaction there. Okay, so this term is going to increase our energy. Okay, which is bad. Remember, increase high energy bad, low energy good, as far as chemists are concerned. Okay. And that's because we've got two negative charges interacting with one another, right? They're going to repel each other. That's our electron-electron repulsion term, okay? So that is what that represents. Okay, I don't know about you, but I really am not super excited to work with this equation as it stands. Okay, there's a lot of things going on here. So I'm going to make it a little bit better and make the assumption that because our nucleus is so much heavier, so much larger than the electrons that surround it, that we can fix the nucleus at the origin. Okay, so this is related to you may have encountered the Born-Oppenheimer approximation before. It's a kind of a similar idea to that, so we'll talk about that more later. But we are, again, just assuming here our nucleus is much larger, okay, much heavier than the electron, so we're just going to assume that this stays fixed. And then we can basically rewrite all of this in terms of just the electron motion, okay, and then we can effectively eliminate anything that corresponds to our nucleus. Okay, so with that assumption, we end up with a little bit of a nicer expression here. So you'll notice that we can essentially get rid of all those terms where we have any mention of our nucleus. Okay, so even though that equation looks better than what we started with, okay, it still is slightly troublesome for us. Okay, so let's get rid of that again. So the problem we have here is that we can't solve the Schrodinger equation exactly for multi-electron systems. Okay, so we've already mentioned this, I think, previously in the semester. Basically, we can only solve the Schrodinger equation for one electron systems, right? So hydrogen, helium plus, lithium 2 plus. Okay, why is that? Okay, well, now that we have this equation in front of us, we can see that it is this electron repulsion, this interelectronic repulsion term right here. Okay, we cannot solve this one. This is the part that gives us trouble. Okay, so everything else is okay, but we just can't properly model that interelectron repulsion term yet. Okay, it's probably not going to happen in our lifetime. So that's what gives us the problem. Okay, that's what prevents us from solving the Schrodinger equation exactly, but thankfully we have developed what we call approximate methods, okay, that can help us solve the Schrodinger equation for many electron atoms. So that is where our variational method, if I can spell, okay, let's try that again. Variational method and our perturbation theory. Okay, so those are the two main approximate methods that we will work with this semester that will allow us to continue on our quantum chemistry journey beyond the hydrogen atom, because, hey, that would not be much fun if we had to stop now. Okay, so we'll save those approximate methods for another video or two. Okay, but for now, I'll just say a little something about another trick that we're going to start using in our treatment of multi-electron atoms, which is the use of what we call atomic units. All right, so we usually think of energies in terms of joules or bond lengths and things like that in terms of picometers or angstroms, and charges on our electron, right? We have specific values for that E value and our mass of our electron, right, in kilograms, okay? So as you can imagine, the calculations can start to get pretty cumbersome with all of these quantities in our multi-electron systems. Okay, so it really simplifies our notation quite a bit when we convert everything into our dimensionless units that we call atomic units. Okay, so these are the definitions of the units that we're currently working with. So in atomic units, we would say that h bar is equal to 1, the mass of an electron is equal to 1, the charge on the electron is equal to 1, and that permittivity of free space, the 4 pi epsilon naught quantity, is also equal to 1. Okay, so again, it's just kind of a simplification tool that we can use to make our notation and our calculations a lot. Okay, so if we incorporate atomic units into our Hamiltonian for the helium atom, okay, we can see that it simplifies nicely with our atomic units into a relatively manageable expression. Okay, so we will, from here on out, be working a lot with atomic units, so please make sure that you become familiar with the atomic units that correspond to the different quantities. One thing that I will also note is that the other benefit to using atomic units, other than just simplifying the expressions and calculations that we're working with, is that it ensures that our calculated quantities that we end up with aren't going to change with future revision of some of these fundamental constants, right? So if we get better values for Planck's constant, better values for the charge on an electron or the mass of an electron, okay, we're not going to have to go back and redo all of our calculations. Okay, so that's another part of the beauty of using atomic units. Okay, so here's a table reproduced from your book. Okay, just gives you a nice summary of the various atomic units and their SI equivalents for things that we'll be encountering in the rest of our journey this semester. Okay, so just one couple things to point out. So notice that the length, atomic unit of length, is the Bohr radius. Okay, that A naught. So you'll see A naught pop up a lot in a lot of the expressions that we use from now on. And then remember that we have the new unit of energy of the Hartree, okay, as we're starting to deal with our atoms. Okay, so you'll see a lot of expressions that come out in terms of Hartrees. Okay. All right, so that's it for just introducing our new model for our helium atom and the idea of atomic units. And you'll have some other videos that will walk through the approximation methods that allow us to keep doing calculations for energies for systems that we can't solve the Schrodinger equation for exactly. Okay, so all is not lost, and you'll get lots of practice with this. All right, hope that was helpful.